Okay, so let's continue with things we were seeing with Laplace equation, Green's identity. So these are the topics. Laplace's equation, Green's identity, and of course, the use and several versions of Green's function. So last class we saw something which I like a lot. The use of Green's third identity to deduce the following. Order of omega, and we got, so we'd be used, or use of, no, that's correct, use of Green's identity to get this. The notation I used was like that. Or maybe I used somehow maybe a slightly different notation. Doesn't matter. Okay, where x belongs to the border. Okay, and we have this. Checking here the notation if I have it right. If we have a corner. And maybe I forgot to write the following last time, which I don't even think it's here in the notes. So let me add. Okay? Maybe I think it's not even in the notes, and I didn't write last time. So what does this say? So maybe let me even fix this picture here. Sometimes actually for my wave problems I have corners. So you see, we can have a point x bar here. This is the internal angle. Let me highlight it. We can have a point x bar here. This is the internal angle, pi, right? And if we have a point in the interior, this theta is 2 pi. So it's a little bit, it resembles, you see, when we did what I called extracting the singularity, right? We didn't do it in all detail. I motivated at least for corners, right? but we did it at the interior. So we had this formula now works for points inside and outside. Why? The first calculation we did in all detail was for a point inside. Remember? Well, we had a ball of radius epsilon, and we did the zoom in. Okay, so let me put it like this because dotted meaning, look, this is just to indicate, right? So when we zoomed in, we saw the effect of the Green's function on that point using Green's identity, and we deduced then Green's third identity, which was 2 pi, okay, and the k is the Green's function, which was log of r. So we needed the 2 pi in sort of to get the delta function. So what that said, now look, we're experts. Now we can read this expression or this like sentence for points inside or on the border. Inside, it means that a point inside the domain, the solution, is given by the superposition of a double layer potential and its density, where this, let me indicate like this is the Dirichlet data, plus a single layer potential having the density of these singularities being the Neumann data. So on the boundary, if we know this and that, we know the solution. Okay? Then we took this point to the boundary. We took this point here to the boundary, the point to the boundary, and then we got this expression where then on the boundary, if you're at a smooth point of the boundary, you get pi. If you're at a corner, you get the internal angle. Well, pi is like the internal angle, right, for something smooth, as I indicated here. So actually these three guys, these three type of points, corners, smooth boundary, or inside, this value here of theta rings a bell, like reminds us a little bit if we're in 2D, right? This I did, but if we're in 2D, and then in 2D we usually put a little round thing indicating it's a line integral, right? Going like this. This is actually, sorry, I didn't mention, but this is actually the picture for 2D, right? As a line integral, or else we're on a surface. But right, this is calculation for D. What I wanted to say was, that this reminds us, having our mind set into D in complex variables, looks a little bit of getting something like residue theorem, where sometimes, depending on the contour, we get half of the residue. Do you remember integrals in complex variables that sometimes does things like that? Right? And then here, if you go below or if you go above, you get half of the residue and so on. So this a little bit reminds us these kinds of ingredients, right? In complex variables, sometimes you can have corners and so on. So let me erase this. Okay? So this is a very nice formula. And the other part of the formula, which I'm not so sure if I mentioned last time, but if I did, was fast, okay, is the following. Let me put I think I maybe did, but not so sure, is that if this is on the boundary, this is also Dirichlet data, okay, and this is a functional relation, okay, so you can think of this as the identity operator, right, acting on the function. So we can basically have a functional relation. So we can have a functional relation between the Dirichlet and Neumann data. And I think I wrote this. So if I pull this on to the other side, I can think of this as an identity matrix if I discretize, so numerically, Let me put it this. This course is not numerical, but you'll see what I mean. Numerically, we can get that identity matrix plus, I'm calling this MD matrix for the Neumann data. No, sorry, the Dirichlet data, let me call this F, is equal to an MN times G with this Dirichlet this is Neumann data, Dirichlet data on a grid, which means we discretize this, we put points. Okay, so this is a vector. And then, right, I'm just giving you an indication. So then this functional relation between a matrix type relation, where it's an identity plus something, which is the identity plus, this is going to become a summation, right? Summation of a matrix times a vector. Look, a matrix like two, quote unquote, two indices, right? Matrix times a vector, plus a matrix times a vector. What I'm calling here is this is f of x, the Dirichlet data. I'm calling this g of x, the Neumann data as I did before. I'm going to organize these discrete values on the vector, either for the f or the g. Now, if I'm doing, this is not, sometimes not so straightforward numerical problem, but still, the idea is here. If you give me the Dirichlet data, you say, André, we're solving a Dirichlet problem. Okay, that means I have this, right? And my problem becomes, let me write here, like b equals to ax, right? This is the b, because I know this. This is the a, and if we can solve this problem, I find my x, which is my g. And then once I find this, I have both f and g on the boundary. I know my solution inside by putting 2 pi. Right? So this is like a boundary integral formulation. So this is a way that I can say, we already know you cannot give Dirichlet and Neumann data at will. So if you give me one, I get the other one. So if you give me the Neumann data, then I have to invert this matrix and I get the f. So then I have the system which is ax equal to b, right? In this way, just showing you that it's revert. But not always. So sometimes this problem is ill-conditioned. For those of you who know a little bit of numerical analysis, right? It's ill-conditioned. Condition number of these matrices can get big, and so and so. Anyway, but the idea is here, and this is not a numerical course. Okay, so this is also to stimulate that we have these two possible integral equations, right? And depending on the type, you have what's called a Fredholm equation of the first type or a Fredholm equation of the second type, depending on if you have this identity guy here, and then theoretically you have to see, right, the solutions, I mean the conditions for a Fredholm equation to have solutions. So this relates to, it's like this, okay? Okay, I'm not going to get much into this here, but these Fredholm equations are in the continuous sense, okay? Or, of course, it has its discrete analog. What I want, at least here, is that we have this relation between Dirichlet and Neumann data, and we also have, I was almost forgetting, the physical interpretation of this, as I mentioned last time, that this guy is a Green's function, has singularities. This guy is its derivative, also has even, say, worse singularities on the boundary, if these 2 points are on the boundary, okay? So this is called a single layer potential. As I mentioned, from electrostatics, it's like a charge, If it's positive, it's a charge like this. In fluids, it's like a source of mass, right? If it's negative, it's a sink. From physics, it's either a positive or negative charge. And this guy here is, the figure is like this. So this is like from electrostatics. This is a charge. And this is the dipole. Okay? So it would be something like this. Right, and here will be like this. Okay, which a dipole is a double layer potential because it's two charges, positive and negative, colliding but without canceling and so on. I mean, you can find this in, if you want, I can give you references, but you can find this in physics book or even some math books too. Okay? All right, so this is a quick review, but important from last class. So let me do a quick now presentation on something which you see, of course, in full detail and things like that in the functional analysis courses here at IMPA. For example, the course PD's linear theory, which is, let's see, a little bit of just a brief introduction to what does it mean to have a weak derivative, okay? Or a derivative in the sense of distributions, so that we see also what the Green's function is doing and so on. Okay. So as references, I'm using some things in Fritz John, but also you can look at in more detail also at the book by Evans, which is the functional analytic book that I gave as reference, okay? But I'm going to give just a brief introduction so that we see. So let's look at this. What is a weak derivative? Let phi of x be our test function, which is a function which we're going to call it in this set script D. This is just a calligraphic D, which is functions which are smooth and of compact support. Okay, so this means, let me put here to be sure as, whoops, sorry, as derivatives of all orders. Compact support, and these are called our test functions. Okay, so basically it's compact support, it's zero outside a bounded set. You know, if you want to look this in more details, you find examples in Evans. Yeah, I have the page here, mollifiers and so on. So you can look at, for example, Evans pages 629 if you've never seen this. So there is a smooth function, right? A smooth function like an exponential. There are examples with exponentials, right? That goes very fast to zero. So it has compact support and it's infinitely differentiable. So using these test functions, we can take the following integration by parts, okay, which is simple for classic functions. I mean, trivial, right? So take this integration by parts, and we will see why this is of interest. Okay, so we're going to now basically just out of curiosity, who here already heard of weak derivatives, of derivatives in the sense of distributions? Maybe you might have already heard of it, but who has studied it? Some of you have. Okay, good, but not all. But that's okay. So it's, for example, we're going to, at one point today, I think I'm going to have time, I'm going to compute the derivative of a Heaviside function. So it's like a little bit computing the derivative of a jump, of a shock, right, as we saw. So it's important to see this. So it's going to be seen in a non-local fashion, in an integral fashion, and that starts with this very simple formula here, which is just integration by parts. Okay, this is integration by parts. And why don't I see, as we did before for Green's identity, why don't I see the parts on the boundary? I don't see it because this guy is compact support, right? That's already a benefit, right? So this minus comes from integration by parts, and basically this is trivial if we have just, for smooth functions. But we're going to use this as our definition for a weak derivative of this guy, of f, if f is not smooth. We're like somehow throwing the derivatives on the test function. So here it comes, okay? So this is trivial. Say if f is C1, has a derivative. But, let me see how I'm right. When f does not have a derivative, we will use this expression to say that, and then I'll come with the definition right now, to say that, I put here, dot, 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 and we continue here, that V is the weak excuse me, derivative of f, or derivative in a generalized sense if this is true for all test functions. Okay, so basically, the function V, that satisfies this is then the weak derivative of f. So derivative in sort of in a non-local sense. And so this is derivative also in the sense of distributions, right? Okay, and you can see that that was sort of maybe an important name here. Let me not make the honors of Laurent Schwartz was a sort of person, the founder a little bit that developed this field, started developing this field. So you see, it's a bit of it's interesting because it's a bit. I mean, these are not weights, right? Because it doesn't have total mass 1, whatever. But it looks a little bit like a weighted sort of derivative, right? So if for all these compact supported functions, this works for all of these guys, then this function here, we'll do this for the heaviside function. This function here is the generalized derivative of f because of this expression, right? Because this guy here at first does not make sense if it has a jump. Okay, so saying just a little more is that we can then say that we can define functionals with f, as, let me use this space to be more, so using notation of operators, let me write this functional. For all phi of this class, so we can define this functional, right? So this is like a definition. Think of the, right? The definition, this is a function. You give me a function f, this is a linear functional. So when I write this for short, right, this guy acting on this guy is basically doing this integral here, okay? And out comes a number, okay? So we can also define this. Okay, this is the function related to the weak derivative of f, right? Which is the derivative in the sense of distributions. So, very quickly, if you think of some examples, right? Because I mentioned about the delta function being the generalized function, I can write this as a functional, as that, which is the Dirac delta function. Which is a generalized function. And where we have the specified that it has total mass 1. So it's the impulse that we learn, even in OD sometimes, right? We learn, this comes many times, we think of this as an impulse. And if this is the point C, sometimes we see it like this, right, as an impulse, something over a very short time, total mass 1. Sometimes we can see it sometimes also like this, saying use a Gaussian, which is total mass 1, where the amplitude as an epsilon goes to 0, right? I'm not going to write the epsilon 0, but as this shrinks, this grows, so that it has total mass 1, which is very simple. This one also shrinks, and the amplitude grows, so it has total mass. So many ways of sort of writing this guy before it becomes the Dirac delta function. And it is, right, this works, let me say, works fine for even continuous functions. And let me sketch this for you, since I have it in the back of my notes, so I don't think it has come out in the copies. Doesn't matter, right? So look at this. So we have this. This generalized function here is a function d phi of x, which is 0 for x in the limit, right? This guy shrinks. It's 0 for its infinity at a point 0 for x different from 0 from c. So for continuous functions, so words for continuous functions say f. So what I want to say is this. The exercise is this. Take dx, and we want to show that this gives us, right, with those properties, this gives us, this is the function of the delta function, right? Using that definition, this would be the functional of the delta function, and we use the properties that this guy has total mass 1 and is 0 outside the point, blah, blah, blah. And we want to see if we get this for the F. So let me put this. Okay, so right, this is just a fancy way of writing 1, right? This is the definition of the functional for the delta function. Okay, this is going to be smaller or equal. Well, actually, first this is going to be equal. Well, let me take one step. Okay, look, this I can put inside, right? It's going to be f of x minus f of c. Okay, so this is going to be less or equal to this. Let me copy so. I just skipped a simple step, which right? I think you can see what I did, right? I just put these together inside the integral, and then I broke the integral with a little apart around the small ball and the rest. Okay? A part of small ball and the rest. And this is going to be smaller or equal. I'm jumping one step from the notes too, but you can think of this as an exercise, but I'm telling you in words how to do, right? Okay, and this would end the proof, skipping a little bit, simple stuff, but let me point out to you. So, okay, from here to here, I can see you already got it. This guy is 0. Right, so let me put it like this so you can see. I'm left with this guy here, okay? Because of continuity of F, it's this epsilon, right? And because this is smaller than the whole domain, I put here the whole domain, and this is going to be 1, and we finish, okay? So this is a way to sort of prove that actually we can write this in a functional condensed functional notation. That's what we were doing, right? And at the end, right? At the end, with the Green's function, I mean, we write sometimes this for the Green's function, right? Which are assumed here generalized functions. But we write it and manipulate it just with this very short notation, right? This is just saying that the Laplacian of the Green's function is equal to the delta Dirac, right? And as we have in Portuguese an expression that probably was one in English I didn't remember, but for those who understand what you're saying, half of an explanation is enough, né? So, bons entendedores, meia palavra basta. Half an expression, half of a word is enough. Okay, so now let's do the exercise. Did I do everything I wanted? No, I didn't. No, I didn't. I almost went too fast. So another example, too, is I can write the following. Look. Weak solution of a PDE so in this notation, right, this is the same as writing this, where is the adjoint of L. That is, right, doing all the integration by parts, or in other words, writing this. For all phi, where this we obtain this from integration by parts. I mean, right? This is a differential operator. You do all the integration by parts, which is you throw all the differential, quote unquote, differential burden onto the test function. That's the one who will have to deal with the differentiation. Here it is. But you don't see anything on the boundary because it's compact support. Okay? And in particular, we have that if we have the Laplacian, its adjoint is like this. And I'll repeat something I already wrote. And therefore, we have for the Green's function, V equal to kappa, let's see what's the notation I'm using here, X and Xi. Okay, I already did this. Okay, yeah, and one note. Go back and see that we already had deduced the expression without knowing anything about, right, about weak derivative. We had a few pages ago deduced already this expression when we did the zoom, right, of the domain with the hole and so on, and we got this, which is exactly this, right? Okay, let me go to the other board and do what would be an exercise with the Heaviside function. Okay, and more things along the lines of weak derivatives and so on are things you see, as I mentioned, in the functional analysis course applied to differential equation, which is PDE's linear theory, and then you can see cases, right? I think so, right? In the course, I don't have the syllabus in my head, but you can probably, I think it's shown that sometimes when you prove things for weak solutions, but then you can show that if it's a weak solution, actually it ends up being the classical solution. There are many things along those lines, and also, trying to see with weak solutions, the class of solutions you have, right? Even though they're not classical solutions, but up to where things go. Okay, so example with a Heaviside function. So I'm going to put f of x is h like this. Right, something that switches on at x0. Okay. So let me see how I say this. Let's compute its derivative in the generalized sense. Okay? Excuse me. So we have d dx of f acting as a functional, right? From what we have just defined, this is the same as this, right? The derivative now hits our test function, right? So I can even put it like this, which means the definition, right? So the definition from integration by parts, and as a functional, so that we have the derivative in a non-local sense, sort of a quote-unquote like weighted sense, has to work for all these guys. You basically, this is the functional, you throw the derivative over there, and this has to make sense. This has to be good, has to work for all D, or all phi's in D. But now, let's just, use the definition of the Hebside function and see what we get. Basically, it becomes this, right? Because it's off, and then switches on. I didn't put it here, but everybody knows, right? It's 1. So it becomes this. Okay? But this, right? You integrate, it's going to be minus 0 because of the compact support, right? So this is going to be equal. Let me put it in all detail. This, right, which is the same. Then put this, which is equal, is the same as this. Right, because this is just, so we can conclude and write that df dx, let me see, I'm going to write it, like this, the full notation. Right, so the derivative is the Dirac, using generalized functions. The derivative is the Dirac delta function, which basically, as we learn these things when we learn undergraduate course, like it's the impulse, right? It sort of switches you from level 0 to level 1, right? But you can adjust this, right? It doesn't have to be 0 to 1. You can add something, blah, 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 right? And sometimes one example is if we have a function that's like this, right? I have it in the notes. I'm not going to write all the details. Then the derivative of g is a delta, right? Which we call the intensity of the Dirac delta function, because this is the intensity that makes you go from level 0 to level A, right? Switches you on. Anyway, just things which we've seen before and are reasonably simple. Okay. Let me go maybe to a new board. Let me go back quickly to conservation laws, very quickly. Just so it's very simple, but just for completeness, and get what would be then the weak formulation of our conservation law. And maybe later on in the course, I'll mention about when we have discontinuity in coefficients or whatever, right? Because we saw this in some problems. So for a moment, why? Because I'm talking about Laplace equation. Let's go back to conservation laws. Let's take this in conservative form. So, let me put it like this. If U is classical and phi of xt is a test function, right, with support in D. Let me define this D, this region, which is AB cross 0T. Let me put the domain here. Okay, just in a schematic way, I'm saying like an example of the support of the function. This would be, this is D, and this would be the support. Okay, then we can write the following. As I said, when we need to look at functions which are not classical, I mean solutions which can go into a generalized function, we have to look at things in an integral form. So let's look at our conservation law in integral form. Let's integrate over this domain in xt with our test function. Right? Nothing more than this. This is equal to 0. But so this, if it's classical, this is just trivial, but now we know from the weak formulation that the idea is to throw the derivatives onto our test function, right? Integration by parts. So we can write then this. So I'm basically going to write I'm going to write for this guy and this guy, it's convenient to write the derivative of the product, right? But this is not the derivative of the product. So I'm going to just copy from the notes so I don't do a mistake, but it's the derivative of the products minus the guy that's there too much, right? Which is, what is too much? Is U is d phi dt U. So let me write, you see what I mean, okay? So I'm going to AB integral 0 to t. Just switch the order, doesn't matter. I'm going to write this, look, phi U t minus U phi t, right? Because if I differentiate this, I get this, but I'm getting this too much, so I got to remove that. Okay? As you will see, this is useful. Why this is useful? You can already see why this is useful. Because this is the guy already that gives me the notion of a weak time derivative, because I'm throwing it on the test function. And this guy is good because I can integrate and go to the border, right? So I'll do the same thing with the spatial term. Okay? So this is this, dt dx, plus, now the spatial term, I'll have the spatial integral inside, because that's the one I want to integrate. So this is phi fu x minus phi x fu dx dt. This is 0. Okay? And now at the end, right? So you do the intermediate steps, which is very simple, because you go to the boundary, you get, sorry, guys that will disappear. and we get this, which is our weak formulation of this PDE. In this case, we might have this time term here of the test function. This initial time term here, right? But this is basically the weak formulation, and I'm going to probably later on show you in class, or maybe induce in a exercise to use these things to compute, to see jump conditions for solutions that are not smooth. And here we see that weak formulation. And as a comment, so this is the weak form. So if I call this 1, 2 is the weak formulation of this. Oh, I have to put here that this is satisfied for all test functions, right? Needless to say. And actually, from this formulation, right, one can also, because it looks very similar, one can also recover for example, the Rankine-Hugoniot condition we had for the speed of the shock and so on, manipulating with these things, just as a comment. Okay, now let me go back to Green's function. This was two parentheses that we opened here in the class today, a little bit of quick comments. One about weak derivative and sense of distributions, which is something seen in detail in another course. This very quick reformulation for weak derivatives. We can use this in the future. I might use it. Now let me go back to, again, playing around with Green's functions and things related to Green's functions and seeing more interesting stuff we can extract from playing with the Green's function. So there's already one thing that's almost one of my favorite ones, which is Green's third identity, which has to do with the boundary integral formulation. Now let's see a few more interesting things. Okay, so a question. I already answered this question. Let's see if you remember. Is the Green's function, is the Green's function unique? So let me take a drink of water. If I ask this question to you like this, you might say, André, I mean, what are you saying? What unique in what sense, whatever, but let me leave it ambiguous for you as a little bit of a mental exercise here. And what is the answer? Yes, no, and in what sense? Of course, there's a tip, right? Something that helps is, a clue is that I'm already thinking here in the sense of today's class, right? The topic, it's generalized function, and do I have it on the board? Yes, I do, yeah? So, look. So here's a little bit of a hint, right? I'm talking today, the whole class, Green's function, as a generalized function, blah, 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 as a functional acting on test function, blah, 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 and that satisfies this, right? So, and this, as we'll see, the Green's function also called the fundamental solution because you can use it to express the solutions a little bit like inverting the operator, blah, 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 right? You've probably heard this before and you'll see it again. But now, the question is, have this equation here in your mind, And with just this information, I ask you, is the Green's function unique? So is it the unique solution of something like this that gives me the Dirac delta function? Yes or no? Is it unique? Yes. Yes? No. Why? Add a harmonic function to this guy, and you still have this. The operator is linear. See, it's an easy but tricky question. So the operator is linear. So V, as I will write now, V plus W, where W is a harmonic function, which is Laplacian of W is equal to 0, is still a Green's function because it still gives me the same exact Dirac at that point. So we can take advantage of that. That's what we're going to do. We're going to play with that. Okay? So let W be a harmonic function. And everything nice, right? So smooth, say, even up to the border, doesn't matter. Then G of x, xc, equal to capital K of xc plus W of x is also, sorry, handwriting, sometimes I start getting tired in my hand, is also a fundamental solution. Also satisfies, right? Let me put it here to be complete. Also satisfies this. So we can play with this W to our advantage. We'll see one example now, maybe the simplest one, and then we'll make a few ones a little slightly more complicated. So let's consider a simple domain, which is a ball. The ball centered at C and of radius rho. Okay? And consider this Green's function. Okay, this is a very simple Green's function. So this is the notation I used before when we deduced the Green's function, right? The radially symmetric solution to the Laplace equation. This is just a constant. This is this guy at the border of the ball. So therefore, this Green's function here is 0 on the shell of the sphere. Okay? Okay, so this is a constant. A constant obviously satisfies Laplace equation, right? So, you know, it's that very simple W over there. And we have that G is identically 0 on the boundary, right? Moreover, dg dn, which is the same as dg dr, right? Because normal derivative is on the boundary is equal to this. Let me put this at the boundary, okay? Remember where this is the area of the unit sphere, okay? So using this in Green's identity, let me write it here, we have, so we get that So we get that. So we get, let me put it here, from Green's identity. From Green's third identity, as I mentioned to you, one of the identities I like a lot. So what did I do here? Let's remind ourselves. This is just Green's third identity, where I've used already here that dg, no, Laplacian g is the delta function, right, from the integration of parts. Okay? Now, remember that the first time I did Green's third identity, I didn't, sometimes I say, I just need that u is something smooth. But now, no, now I know that u is harmonic. I'm using that piece of information. So u is harmonic. I'm also using the fact that this g, if it's centered at the ball, right, it's something like this. Right? If it's centered at that ball, g at the border is also 0 by construction, by this super, super, super simple construction. Okay? So therefore, we get, well, unfortunately I have to go to the next board, but it's important because I have to write a title. We get a very nice expression. Very nice expression. One of the many very nice results, right? So now we get for harmonic functions, which is that u over there, Gauss's law of the, let me write it over here, arithmetic mean. Which is u of c and let me do the figure again just so that we don't have to go to the other board. Look what a very nice expression this gives us. Right? Gauss's law of the arithmetic mean. So using that Green's function that is 0 on the border, right? I get this expression, and what does it say? This expression is very nice, so you can think of it as a stationary temperature, for example, or something related to a potential. Why stationary temperature? Because the equation for the heat equation, as we'll see, it's du dt is equal to Laplacian of u. But if it's stationary, right, if you reached equilibrium, it's just Laplacian equal to 0, right? So this says that the temperature or some potential at the center of the ball is equal to the mean of the guy over that spherical shell. This is the area of the spherical shell, so the mean is, right? In words, what the expression says is an integral is a sum, right? So in words, I am summing all the temperature or the potential on the shell, dividing by the area of the shell, and I get the mean. The mean temperature, the mean potential, the mean whatever you have in mind, right? And this expression is very nice. So it doesn't say about the size of the sphere, right? Get a little sphere or a big sphere. If it's a harmonic function, the center, you have the mean, okay? So this is a very nice result. And from this, there are many things that also you see in other PDE's courses here at IMPA. I just mentioned a little bit. I used to give more detail here, but to not repeat other courses, which is maximum principle. There's many versions of maximum principle. So I think see even this in the master's course at IMPA, or the linear theory, PDE's linear theory. Let me just indicate a few things of the maximum principle, right? There's many versions. So so this gives us the maximum principle in a very intuitive way. And this here is what's called the strong version. There's some few versions. You find this in Fitzjohn, in Evans, and so on, which is this. Omega is some open set, bounded and connected. U is C2 in omega, and A harmonic function in omega. Then, this is what the maximum principle says, then either U is a constant, or it attains its maximum at the boundary, or the maximum is attained at the boundary, right? I mean, this is kind of intuitive, right? So if the guy inside is sort of the average of what's around it, right? The average cannot be higher than what's around. So this is the maximum principle, and clearly as a consequence of this. Then, let me say facts or observations, better. Let me put it here, A. We also have a minimum principle. Say, just use V equal to minus U. Right? If V is equal to minus U, it's also harmonic, blah, blah, blah. And right, the maximum will be the minimum. It can be used, right, the maximum principle can be used to show uniqueness. For example, of the Dirichlet problem. So people, for example, in elliptic problems, complicated nonlinear elliptic problems, so many times look, and many times difficult to prove, maximum principles associated to their operators and so on to extract things, for example, sometimes to get uniqueness. In the linear case, it's very easy because you subtract and you get 0. And then another fact, and to gather up, is that I think I mentioned this, take the 5-point molecule, as we call it in numerics. For the discrete Laplacian. So the 5-point molecule, what I mean is this. So this is an expression that gives us a numerical method to solve the Laplacian in the computer. Okay, this comes, so here it is, says that the approximation is h squared times the Laplacian, h squared because we're on a grid like this, or this, and put it like this, or else this is delta y, this is delta x, and we're using the fact that delta x, delta y is equal to h, so it's a uniform grid, okay? So if you do this, delta x, which is this, right, you're trying to solve Laplace's equation on this grid points, it will become a problem in linear algebra, right? Everybody has heard of this. So if you use Taylor series, you can write this. The second derivative in x and the second derivative plus the second derivative in y is basically approximated, right, by this guy. This is the Taylor series expression, but actually, if we want to do this numerically, right, I'm not going to do it here. You just divide this by h squared, and you're approximating the Laplacian. Okay? So, this is the discrete Laplacian. Now, if we're going to do, right, if we want to impose that the discrete Laplacian, right, this is equal to 0, basically I can then do, my approximation will lead to this equal to 0, okay, which is the same that this is equal to this. This is my discrete Laplacian leads to that. Agree? Everybody agrees? Started from Taylor series, which leads to this. Okay? And the nice thing is that the very simple method to solve Laplace's equation numerically has also a discrete maximal principle. Because it's saying, oh, and I forgot to say, why is this called the 5-point molecule? Because this says that the value of the solution here uses, let me put maybe squares, uses this value here, this value here, this value here, and this value here. Look, x minus delta x. I want the solution x, so x minus delta x, x plus delta x, y minus delta y, y plus y. And so that you can visualize, in many numerical books, this is the terminology, right? So you can visualize how the points are connecting in the discrete operator. They call, what is the molecule of the method? The molecule, because it looks like a little molecule. The molecule is this. So it's a little bit on a checkerboard, how 3 is. So this is why it's called the 5-point molecule. 1, 2, 3, 4, 5. Right? So the discrete Laplacian is reduced to 5 points, kind of connected to each other, a 5-point molecule. And you see that this 5-point molecule has something that looks like the maximum principle, or has a little bit of a discrete version of Gauss's law. The point in the middle is the average of its surrounding points, arithmetic average of its surrounding points. And numerically, you can see, nice properties about this, about consequences, but at least, and this is a typical good method to solve Laplace's equation numerically. Now, note the difference of what I point out in this course. This is when you have to solve inside the domain. And we saw up to this point a method, which is the boundary integral method, where you don't have to solve inside the domain. You only have to solve on the boundary. So that sort of reduced our problem from a 2-dimensional problem, x and y, to a 1-dimensional problem over a curve. But as everything in the numerical life is that it's a bit like the short blanket. You want to cover something which is an advantage, there are also disadvantages. And you have to learn which advantage you want to take advantage of and which disadvantage you're able to deal with, right? So therefore, interior methods, boundary integral methods, I mean, they're useful, but you have to know when and why and where, right? Okay, so here's the maximum principle for the discrete case. Okay. Well, you know why? I don't know. Let me give you a quick. Let me give you a quick. Since I have a few minutes, but I'm not going to use all the minutes because we're also going to start Wednesday repeating everything. So scenes from the next class. So scenes from the next class are like this. Today, we had our Green's function, our special Green's function constructed for a fixed point inside and how to make it 0 on the outside. Okay? That was very simple. Next class, we're going to do something similar, but now we will allow the C point to move. You see here, we got things, right? Gauss got beautiful expression, just something, he fixed the center, got the ball around it, showed the arithmetic mean and so on. But now, I mean, we want to allow the whole thing to, in the Green's identity, this point C to be any point and to get. So the question was, how to get G over the boundary identically 0. Note the difference. The problem we did today is we got G on the boundary to be 0 if the source point, the point where the Green's function blows up, is at the center, only for that case. Was that bad? No. That was the simplest case, but it was not bad. It gave us interesting expressions, like Gauss' law is very nice. But now we want more. Allow this guy to move around, okay? And what we're going to see is something that reminds us from complex variables again, even though here is an Rn, is that we're going to be able to construct this G by writing G as our Green's function plus another Green's function, star, but that has a singularity, C star, outside the domain omega. Well, if this Green's function here, K star, has a singularity star outside the domain omega, this is a harmonic function in omega. It's a W, just a fancier W. And this point C here is called an image, or maybe even better, maybe reflection of C about the circle, if it's in 2D, or the spherical shell in general. Okay? And we're going to see what is this thing about the reflection. Well, there are two domains where we can construct this special Green's function like this that's going to be 0 on the boundary. The other one is the half plane. So this is the domain omega. And I'm going to finish here. This is domain omega. I have my point C here. And I'm going to have my reflected point, my image point here, C. And for the half space, this distance here is exactly that distance there. And doesn't this remind you, for those who have seen complex variables, doesn't this remind you the reflection, the principle, Schwartz reflection principle, where to do analytic continuation and so on, you use the conjugate of the point z, right? And the function has to be 0 here, blah, 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 real value, whatever. So these are two cases, and that's why this is also called the method. So I'll come back to this next class. The method of images. So if your boundary is a straight line, the image is the intuitive reflection to the other side, right? If you reflect this, right, it's the same angle. With the reflection to the circle is not symmetric. It has a little expression to it, right? As this guy goes to the origin, this guy goes to infinity, right? But it'll do the job. And then, of course, if we do things right, we have a Green's function that's 0 here. We have a Green's function that's 0 here. And we can take advantage of that for slightly different reasons than we took over there with Gauss's law. Next class. Okay, so actually with this introduction to next class, I used more or less the time I had. Okay, obrigado.